Okay, so let's look at the math for this. But before we look at the math, I want to talk about a couple of things, okay? The first thing is the equation that we're going to be using in order to draw a mole-to-mole relationship between KHP and sodium hydroxide. But before I do that, I want to talk briefly about why KHP is an acid and why it's written so funny. So I don't want you to get stressed out about the structure. You don't have to know it. I just want to kind of illustrate what's happening here. So potassium is a plus charge. This structure as a whole is a negative charge. So KHP kind of acts like an ionic compound. However, KHP, you'll notice that there's a hydrogen up here and it's attached to an oxygen. We call that hydrogen an acidic hydrogen, meaning it can be donated, right? Okay, so what that means is this is the hydrogen that we're talking about that is going to interact with the hydroxide on sodium hydroxide, okay? So if I look here, how I have it written, I have hydrogens here, but then I also have one out front. So anytime we're dealing with an acid, the acidic hydrogen is going to be the hydrogen that's in the front of the compound, okay? So what's going to happen is you're going to react your hydrogen, your acidic hydrogen, with your basic OH, which is right here, okay? And you have HOH, or how we know it as water, okay? Which is just hydrogen and hydroxide. So this is the neutralization that's happening here, okay? And then I don't really care about what the other product is because that's not what I'm actually looking at, but we can write it, okay? The other product that I'm working or that I create is the sodium with everything else besides that acidic hydrogen. Okay, now this is a balanced chemical reaction, which means everybody has a 1 mole coefficient, right? So it's just 1, 1, 1, 1. And that's what I need, right? I need to know the relationship between the acid and the base so I can do a stoichiometric conversion, okay? So you'll notice that I have trial 2 data up here. So I'm going to solve from trial 2 because that was the best data set that we had. You will be responsible for trial 1 and trial 3, and then obviously a conclusion. And your conclusion, and I'll talk about this at the end of the lab. I don't want to get too far ahead of myself, okay? So the question is, I'm trying to figure out what is the actual molarity of sodium hydroxide. That's what I'm trying to figure out. Can I figure it out from this information? Well, let's think through it, okay? So we know that molarity is equal to moles over liters, okay? But this is the moles I need to ask myself is who does this have to be? Well, if I'm solving for molarity of sodium hydroxide, I need to know moles of sodium hydroxide. And we can do that because now we have a balanced chemical equation between KHP and sodium hydroxide. So I can solve for this using stoich, okay? And then liters is what we collected for our data, okay? So then this is that, and then liters is going to be the data that we collected, okay? But it's really important. We need to make sure that we're in liters. So let's go ahead and do that right now. So I'm gonna go 1, 2, 3, so I have to add a 0, so it's actually 0.02175 liters. Okay, so I need to stoich out moles of sodium hydroxide using my KHP. So I'm gonna ask myself, I'm gonna say, just like we did all through honors chemistry. So I'm gonna say question mark, what am I looking for? Well, I need moles of sodium hydroxide, so that's what I'm gonna put. Moles sodium hydroxide is equal to, what's the given? Well, it's how much KHP I weighed out. So I weighed out 1.022 grams of KHP, okay? Now, the next thing that we need to do, figure out the molar mass of KHP, okay? Here's the cool thing about when you do labs. You don't have to calculate the molar mass using the periodic table. The chemical bottle that you're using has the molar mass on it. So if you look right here, it says FW, which means formula weight, is 204.23. Okay? So I'm going to ask myself, what is the first unit that I have to cancel? I have to cancel grams of KHP. So that's going to go on the bottom. The only relationship that I have to grams is moles. So moles of KHP will go in the top. We have to remember that this is our molar mass conversion. So for every 1 mole of KHP, it weighs 204.23 grams. Okay? Grams of KHP cancels, but I still have moles of KHP. I need moles of sodium hydroxide. And I can do that because I have a balanced chemical equation. Okay, so I'm going to do another conversion. What do I need to cancel this time? I need to cancel moles of KHP. So it goes in the bottom. What do I want? I want my question mark, which is moles of sodium hydroxide. And since I have a balanced chemical equation, I can draw a relationship between their moles. And since it's a 1-to-1 ratio, for every 1 mole of sodium hydroxide, I need 1 mole of KHP. So then if I plug this into my calculator, times by the top, divide by the bottom, so ultimately I'm just dividing by 204, divided by 204.23. Nope, I did a big number. I did 5. I'm getting, with 4 significant figures, because that's what I have with my data, 0.005004, and this is moles of sodium hydroxide, which is awesome because that's what I need for molarity, right? So now I can just plug it in over here. I can say equal to the moles, which is 0.005004 moles of sodium hydroxide divided by my liters, which is 0.02175 liters. And that gives me this is beautiful, 0.2301 molar sodium hydroxide. Okay, so we thought we made a 0.25 molar sodium hydroxide solution, but it turns out that we were a little low. And that makes sense, right? Because the water was attaching to the sodium hydroxide pellets, making it more diluted, right? So we have a lower concentration. So our concentration is 0.2301 molar. So that's for trial 2. You are going to do the math for trial 1 and trial 3. If either of those are way off this, you can eliminate them. If it's close, you can add, divide, and get an average. And then you need to calculate percent error because it's supposed to be 0.25 molar. Okay? Hope this helps. And thanks for watching.